Imagine a web server handling 10,000 open connections at the same time. Each one is a client waiting for a response, and the server has to know right now which ones actually need attention. The system call that makes this practical on Linux is called epoll, and it's one of the core reasons Linux dominates high-performance networking. Every network connection on Linux is represented as a file descriptor, just a small integer that the kernel uses to track it. The tricky part is that most of those connections are idle at any given moment. A chat server, for example, might have 10,000 open sockets, but only 20 actually sending data right now. The naive solution is to spawn one thread per connection and let each one block on a read call. That technically works for 100 connections, but at 10,000, you're burning gigabytes of RAM on thread stacks, and the CPU spends more time switching between threads than doing real work. The first step forward was select and pull. Instead of blocking on one socket, you pass the kernel a big list of file descriptors and say, tell me which ones have data. The kernel checks each one and returns. That's better than threading, but there's a cost you feel at scale. Every time you call select, the kernel copies that entire list from your process into kernel space, then scans every single entry, even if 9,000 of them are idle. You're paying O of n on every event loop iteration. At 10,000 file descriptors, that copying and scanning happens hundreds of times per second, and it starts to drag. epoll fixes both problems with a simple design change. You create an epoll instance once, then register your file descriptors with it also once. After that, you call epoll wait, and the kernel puts your process to sleep. When any registered socket becomes ready, the kernel wakes you up and hands back only the sockets that actually need handling. No copying the full list, no scanning idle sockets. You handle those connections and call epoll wait again. That's the entire loop. The key difference from select is that epoll remembers your FD list inside the kernel. You register once, and from then on, the kernel tracks changes internally using a red-black tree and a ready list. When data arrives on a socket, a callback adds that FD to the ready list, and epoll wait just drains that list. It's event-driven at the kernel level, not a repeated scan. Here's the pattern in Python, which wraps Linux's epoll directly. You create a TCP server socket, bind it to a port, then create an epoll instance and register that server socket for incoming connections. The main loop calls epoll.poll, which blocks until something happens. When the server socket itself is ready, that means a new client is connecting, so you accept it and register the new connection with epoll2. When a client socket is ready with data, you read it and echo it back. If the read returns nothing, the client disconnected, so you unregister the FD and clean it up. Notice there's one thread. No thread pool, no icing framework, just one loop handling thousands of connections because epoll wait only returns the ones that are ready. This entire server can handle 10,000 idle connections for the cost of keeping their file descriptors open. The reason epoll handles 10,000 connections or 100,000 without flinching is that its cost is proportional to the number of ready connections, not the total number of connections. If 10,000 sockets are open, but only 3 have data, epoll wait returns 3 file descriptors. Select would have scanned all 10,000. There's no list copying on each call because the kernel already has the list. In benchmarks, epoll handles over 100,000 connections per second on modest hardware. This is why Nginx chose epoll for its event model, why Redis uses it for multiplexing all its clients on one thread, and why the Go runtime and Node.js use it under the hood on Linux. If you've written a network service in the last 15 years and it performed well on Linux, epoll was probably doing the heavy lifting. That's epoll. Register once, sleep until something happens, handle what's ready. It's the reason Linux owns the high-performance networking space, and now you know exactly how it works. Thanks for watching Awesome Linux TV.